Hi, everyone, and welcome to today's live session, Design and Application of a Pressure Sewer System. I'm Rachel Seiler, today's host and Marketing Communications Manager for E1. Before we get started, some housekeeping notes. All attendee lines have been muted. We'll be recording today's session, and an archived edition will be available on E1's website and our YouTube channel. Upon successful completion of today's webinar, you'll receive a PDF of the presentation as well as a certificate of attendance. And finally, we'd love to hear from you. We've allotted about 10 minutes of Q&A during today's session, so please open that Q&A window in your webinar controls to make use of that feature. And if we don't get to all your questions, we'll answer them in a follow-up email. So now, without further delay, I'd like to introduce today's featured presenter, Derek Latchett, Director of Engineering for E1. We're in for a treat today. Derek has worked with E1 for more than 10 years and has been involved with project management, sales, post-sales support, local manufacturing support, and contract management. Derek was involved in many pressure sewer projects in Australia and New Zealand, including Mornington Peninsula, where 16,000 properties are undergoing a septic-to-sewer conversion. He holds a bachelor degree in mechanical engineering from Case Western Reserve University and a master's degree in engineering management from Clarkson University. Besides E1, Derek has held various engineering and operations management roles in aerospace manufacturing companies within E1's parent company, Precision Cast Parts Corp. Derek, take it away.
Hey, thank you, Rachel, and welcome everyone. I'm glad you could join us today. I'm really looking forward to reviewing the origins of pressure sewers, the applications and benefits. Then I'll review some of the unique characteristics of the E1 system that it's made it so successful. We'll examine some case studies and how E1 designs pressure sewer systems. This webinar is specifically targeted for engineers, and we will review some more advanced pressure sewer design topics to give you the tools you need to stretch pressure sewers into new applications. We'll round out the session by discussing construction, operations, and lifecycle cost analysis. We got a lot of material to cover, so let's get started. Briefly to introduce E1, E1 and pressure sewers have existed for over 50 years. E1 is a US-based company and headquartered in Niskayuna, New York. It's approximately 2.5 hours drive from New York City. The facility is over 85,000 square feet and houses 120 employees. E1 is predominantly involved in pressure sewer systems, as we'll review in length. E1 is also involved in the energy sector through the design, engineering, and manufacture of hydrogen auxiliary systems for power plants. These two industries support critical infrastructure around the world. The history of E1 begins with the development of the concept of pressure sewer systems. In the 1960s, what became the United States Environmental Protection Agency and the American Society of Civil Engineers, an organization that might sound familiar to many of you, were tasked with solving some challenging problems in wastewater collection. Through their work, the concept of a household appliance to perform the task was conceived. Engineers from General Electric were engaged to help. This is the same GE that manufactures jet engines and medical imaging equipment, locomotives, etc. GE also manufactures household appliances, and engineers from that department developed the first sewage grinder pump for pressure sewer systems. After the completion of the project, GE wasn't interested in commercializing grinder pumps. However, the engineers working on the project saw great potential for the grinder pump and pressure sewer systems. They purchased the intellectual property from GE and founded Environment One Corporation in 1969. From those humble beginnings, E1 has become the dominant global market leader in pressure sewer. We have the largest global markets for pressure sewer in the USA, Europe, Australia, and New Zealand. Again, E1 leads the global market that we invented and today have an established global installation base, over 700,000 units installed and manufactured and installed globally. And another way to look at that is over 2.5 million people rely on E1 pressure sewers every day. So that's who we are. Now, why we're here. Fundamentally, our mission at E1 is to spread awareness of pressure sewer as an appropriate solution for wastewater collection. And one of the key ways we like to spread awareness is to engage all project stakeholders as early as possible and discuss how the systems can be designed. We provide design assistance at a preliminary level to develop a budget cost, which can be evaluated against other options, because ultimately, most decisions are based around cost. We will discuss design recommendations and cost analysis at later points in the webinar. E1 strives to earn the title of trusted advisor when it comes to pressure sewers. E1 leverages decades of experience to provide the solutions to simplify challenging problems. Finally, we establish relationships for life with all customers. Our singular focus on pressure sewer necessitates that every project is successful. So what is a pressure sewer system? A pressure sewer system is a sewage collection system. Our job is to transport sewage from point A, usually the source, to point B, which is the discharge, and that can vary, and we'll talk more about that later. But let's visualize the system. At each property connection, there's a collection tank, which contains the grinder pump. This whole station is often referred to as a grinder pump station. Wastewater flows into the property through your standard drainage. This is 4 to 6 inch PVC or 100 to 150 millimeter PVC drainage. After being ground and macerated and pressurized by the pump, the wastewater slurry enters the pipe network. And generally, this pipe network is installed in or adjacent to the roadway with minimal cover or burial depth. The pipe network follows the terrain of the ground as required. There's no slope or grade on the pipe. As shown, the pipe can travel uphill until it terminates into another collection system, or as shown on this image, a treatment system. Pressure sewer systems can be a variety of sizes, from a single property to subdivisions of hundreds or thousands of houses, since there's no large central infrastructure required for an economy of scale, like gravity or vacuum systems. Pressure sewers overcome challenges presented by a variety of terrains. It all comes down to cost, and pressure sewers will nearly always deliver best value for money. As an engineer, I believe that nothing is impossible, but I certainly know that some things are not cost effective. With flat terrain, sewer methods like gravity sewers end up requiring very deep installations and many intermediate lift or pump stations. Those large pump stations are expensive, and deep excavations can require expensive things like trench shielding or sheet piling. Pressure sewers can solve those problems. In wet areas, installing that gravity or vacuum system with open cut trenching, the same cost issues with those deep excavations can be magnified when we introduce the need for dewatering. Pressure sewers can solve those problems, and pressure sewers are commonly found in wet and coastal areas. Rocky terrain is expensive to excavate and requires drilling, blasting, jackhammering, etc. to install that gravity or vacuum system. Pressure sewers, again, solve or at least minimize many of those problems. Finally, hilly terrain means many major pump stations at the bottom of the hill. Pressure sewer systems can defy gravity and enable development and sewering in many hilly areas. The last application is using pressure sewer as a tool to expand the service area of an existing collection system. This results in a hybrid system where portions of the project would be serviced with, say, a gravity collection system, but the most challenging areas can be solved with a pressure sewer system. We'll actually look at this in more detail in our first case study. There are three basic categories for pressure sewer project. First are projects where existing on-site treatment or holding systems like septic tank or cesspools are no longer functional. Could be due to the breakdown of the structure or changes in the environment. Pressure sewers are often used as a cost-effective means to allow a municipality or authority to eliminate these failing systems. The other large segment of the market is new land development. Pressure sewers will be shown to provide land developers with the opportunity to cost-effectively sewer the new development. Pressure sewers can unlock land that may have otherwise been unserviceable or accelerate the development timeline. Finally, pressure sewers are used to replace existing collection systems. Similar to the septic tank replacement approach, pressure sewers are used when an existing collection system has reached the end of its useful life or the cost to maintain that system becomes too great. When comparing the life cycle costs of renewing a gravity system versus the costs of installing a new pressure sewer system, the whole of life costs for the pressure sewer systems are often lower. And we'll talk more about system and life cycle costs later in the webinar. Beyond the constructability, pressure sewers have a variety of other benefits. Pressure sewers don't require any large, expensive, and critical central infrastructure like that major gravity pumping station. This reduces costs and defers risk. Debris plagues every wastewater operator around the world. Things that are not supposed to be in the sewer system end up there. This is a relevant industry and social problem, and really best solved by education of end users. However, practically, it's never going to be completely solved. E1 grinder pumps perform well with most types of debris, but when the system is abused due to high amounts of debris, this can create problems with any grinder pump. However, the problem is nearly always isolated at the grinder pump and not inside the pipe network. Repairs are isolated and the system abusers can be dealt with directly. Finally, the materials and methods used in pressure sewer systems result in a sealed system. There is practically zero stormwater infiltration. This reduces costs and risks of overflow during wet weather common in other collection systems. Next, let's briefly review some technical details of pressure sewer systems, E1 products, and some key differentiators. This is a cross-section view of a grinder pump station installation. The grinder pump station is typically located within the property boundary, and that minimizes the length of the private drainage, which I often consider to be the most vulnerable part of any wastewater collection system. The unit shown here represents one of many types of grinder pump stations that E1 manufactures. There's a variety of different configurations, geometries to satisfy operational, regulatory, and logistical needs, but the general operation is identical among all models. Wastewater flows into the collection tank, and the grinder pump automatically detects when the water level reaches a predetermined level. The wastewater is macerated and pressurized. It's then discharged through a small diameter line. At this point, we're talking about an 1.25 inch or 40 millimeter line. There's a valve assembly referred to as a lateral valve or sometimes a boundary kit, which features a flapper type non-return valve and an isolating ball valve. The wastewater enters the common main, which again is located in or near the roadway. The diameter of the common main will vary based on the hydraulics of the system, the number of pumps connected, the pressure in the main, elevation changes, etc. We'll talk about main sizing when reviewing the design method. And as a point of information, it's not uncommon to have a pressure sewer project with hundreds of connections into a common pipe network where the largest diameter might be less than 4 inches or 100 millimeters. The equivalent gravity sewer for a project like that would be twice that diameter. The final portion of the system to mention is the alarm panel, which is mounted to the side of the house. All of the level sensing control devices are integrated into the E1 pump itself. So E1 doesn't typically refer to this as a control panel since it really doesn't control the pump. Its primary purpose is to provide a visual and audible alarm if there's a high level in the tank. This alerts the property that there may be an issue with the system and service is required. Regardless of the tank configuration, the common element is the grinder pump. The E1 grinder pump, often referred to as the core, can be considered the heart of the system. It's a 1 horsepower or 0.75 kilowatt single-phase pump. Unique to E1, this pump features a large diameter grinding device, which delivers best-in-class performance. E1 utilizes a progressive cavity positive displacement type pump, and this allows a relatively small pump to generate high pressures. The E1 pump is designed into systems to operate up to 185 feet or 56 meters of head. This facilitates that uphill pumping and pumping across long distances. A single E1 pump through an 1.25 inch line can pump nearly 2 miles in a straight line. Increasing that pipe diameter will increase that distance. The E1 grinder pump has an integrated design unique to the industry. The level controls and motor controls are incorporated into the pump. This results in a modular design, which is quick and easy to install and interchangeable at any site. Finally, the E1 grinder pump is designed with robustness and reliability in mind. Much like any other appliance found in the home, the E1 grinder pump does not require any routine preventive maintenance. It's a run-to-failure device. There are wearing items in the pump, and E1 expects these to last on average 8 to 10 years in a residential application. This minimizes the operational cost and the burden to operate and maintain the system. As mentioned, E1 utilizes a progressive cavity pump design. The progressive cavity design, also referred to as the Moineau Principle, generates a practically consistent flow rate against a wide variety of system pressures. This simplifies the design and ensures that flows are consistent and predictable. The grinding capability of the E1 grinder pump is paramount to performance. It's right there in the name, grinder pump. Operators around the world, again, struggle with debris and wastewater networks. The E1 design offers that best-in-class grinding performance when faced with household goods. The large diameter cutter wheel creates a low inlet flow velocity. This causes debris to be gently exposed to the grinding face. Debris is processed through the small bites. This results in resistance to a blockage or a jam due to debris. In contrast, most other designs feature a small grinding device, creating a high inlet velocity. Debris is rapidly sucked through the grinder, which makes for great YouTube videos, but the reality is that it increases the likelihood of a blockage, especially as that grinder loses the sharp edge. Speaking of a sharp edge, the E1 grinding device does not rely on a sharp edge. It's a true grinder. That low inlet velocity, along with grinding design, creates the best-in-class performance. The alarm panel provides an audible and visual alarm when a high level occurs. The alarm panel's lights illuminate and buzzers sounds. This indicates to the resident that there may be a fault condition within the system. And depending on the ownership and operation model, the resident would notify the municipality or a service provider to investigate. E1 alarm panels feature a variety of other functions and also offer cellular telemetry options to provide remote alarms and notifications to a service provider. The capacity within the tank provides sufficient storage for residents to continue to use water within reason until a technician arrives. And again, E1's documented mean time of service of 8 to 10 years means that in general, this alarm system will only need to operate on average every 8 to 10 years. So now that we're all experts on the background of pressure sewers, the benefits, applications, and products, let's see it in action. The first case study we'll examine is how an E1 pressure sewer was utilized in a new land development project. To review pressure sewer benefits, specifically to builders and developers, pressure sewers help overcome geotechnical challenges like terrain or poor ground condition. This can be critical and allow land to be developed that couldn't be serviced cost effectively with other methods. Pressure sewers are much faster to install than other methods. Small diameter materials, shallow installation, non-critical slope means that the land can be made available sooner. In many cases, pressure sewers can help defer costs associated with the sewer system. The developer's contribution may initially only be the pipe network. The cost for the grinder pump station would occur during home construction. And sometimes the cost of the grinder pump station can even be passed along to the builder or buyer of the home. Finally, the environmentally sensitive nature of pressure sewer systems can maintain the natural beauty of a development. The sealed network means no overflows and minimal disruption to any existing vegetation. The first case study is Promontory, a residential development near Park City, Utah. This development consists of over 1,800 residents with beautiful scenic views of the surrounding mountains and valleys. The population around Park City and throughout Utah is quickly expanding, and land developers are eager to bring land to market quicker and cost effectively. The developer faced some challenges at Promontory. The real estate is very valuable, and the developer was eager to move forward. However, the geology of the area didn't lend itself to traditional excavation methods. The rock in the area was, as the engineer described, plasticky and didn't respond to impact or blasting. Installing a gravity sewer in parts of the development was really cost prohibitive. In fact, with the extent of rock drilling required, it was cheaper for the installing contractor to purchase rock drilling equipment than it was to rent that same equipment. Most of the development could be serviced cost effectively with traditional gravity sewer. However, some of the most picturesque lots could not be serviced without adding lift stations and running sewer lines through the back of lots. The E1 pressure sewer solution. Promontory is an excellent example of a hybrid gravity and pressure sewer solution. 6 lots that were below the grade of the main gravity sewer were serviced with an E1 pressure sewer system. Each property received an E1 grinder pump. This approach eliminated those additional major lift stations and those backlot sewer lines. This saved the developer money, reduced the operational burden to the water district, and fundamentally reduced risk to all stakeholders. This hybrid approach is common with new users to pressure sewer systems. The E1 solution can often save the development. And once the developer, engineer, and contractor see the capabilities and simplicity of a pressure sewer system, they're often eager to use it again, but this time for the whole development. The pressure sewer system delivered the architectural flexibility to locate the homes on the lot. Remember, E1 can defy gravity and avoid deep excavation. This enabled the best and most scenic use of the land. The E1 solution provided the developer and home buyer with a reliable and environmentally friendly solution. We'll have another case study later, but let's dig in now on how pressure sewers are designed and how E1 can help. The E1 approach to system design follows these general steps. First, we need to ensure we have all the relevant information. This is critical since the quality of the output of the design is a function of the quality and accuracy of the inputs. The next step is to break the project into small segments or zones. Each zone is examined separately, and then the analysis considers how all the zones operate together. In an E1 design or application engineering study, a zone is a section of the pipe network where the design flow increases. Flow increases due to a change in the number of pumps operating simultaneously, more on that in a bit, or when two branches join and create a downstream zone. This webinar does not review the zone division process in detail. If you do need help understanding what zones are and when they occur, check out some other of the webinars hosted by yours truly. These are available on E1's YouTube page or linked at e1.com, or feel free to reach out to E1 and our global network of distributors with help on your project. Next, a total dynamic head or TDH calculation is performed to ensure grinder pumps can operate within the network given friction losses and elevation changes. The network pipe sizing is selected for each zone and modified to ensure a sufficient flow velocity is achieved and to minimize the retention time. And the best news is that most of these calculations and modifications are easily performed using a free tool called the E1 Design Assistant. The E1 design method is referred to as the probability method or simultaneous operations method. This method is based on a statistical model developed from empirical data. It shows that given a total number of pumps, there will be a statistical maximum number of pumps operating simultaneously. And this statistical model creates the table shown on this slide, the maximum number of simultaneous operations. So given a total number of pumps in the left column, there will be a maximum number of pumps operating simultaneously in the right column. So say we had 100 pumps, that would fall in the 81 to 113 range. Our simultaneous operation tells us that there will be 8 pumps operating simultaneously. Simple as that. Another critical assumption, an element of the E1 design approach, is a consistent flow rate from each pump, and that positive displacement pump delivers a relatively consistent flow rate regardless of system pressure. And this allows for a linear relationship between the number of simultaneous operations and the flow in the pipe. So back to our example. If there are 100 pumps operating, 8 are going to operate simultaneously. And we know that an E1 pump will produce approximately 11 gallons per minute or about 0.7 liters per second, regardless of system pressure. That means I know the flow rate through the network at that point will be 8 times 11 or 88 gallons per minute. This becomes the basis for other calculations like velocity and total dynamic head. The SimOps method cannot be used with systems incorporating centrifugal pumps. The simultaneous operations method was developed by E1 and has been utilized for decades. The method is codified by regulators around the world, used daily by E1 and countless other users, and the methodology is defensible and supported by historic and modern real-time field data. So now that we have our project information and we understand the assumptions, we can begin the design process. The design process is a combination of 1, manual work, such as creating zones, measuring zone lengths, and understanding elevations. 2, data entry into Design Assistant or performing the calculations. And 3, interpreting the outputs of your calculations or from Design Assistant. Design Assistant is, as described, an assistant. The software performs many of the calculations to provide the user with insight into flow rates, velocity within the pipe network, and pressure total dynamic head. You can perform these same calculations with pencil and paper, calculator, spreadsheet, whatever. But Design Assistant comes prepared to do all the calculations for you. Design Assistant also performs a series of iterative calculations and outputs an ideal pipe size for a particular zone to maximize system longevity. All of these functions, plus some commercial considerations, are packaged by Design Assistant into a report or study. Now, any discussion about what Design Assistant does wouldn't be complete without a discussion about what it doesn't do. Design Assistant does not design the system for you. The software does not create zones, and the software assumes essentially consistent flow, and it doesn't perform any sort of dynamic flow modeling. Furthermore, since Design Assistant utilizes the simultaneous operations flow assumptions, Design Assistant won't change the number of pumps operating simultaneously if you increase the flow from a dwelling or a connection. Simultaneous operation is only a function of the number of connections or pumps. Design Assistant is utilized for designing the pipe network and does not design pump stations or provide sizing of the grinder pump stations. If you do need help with sizing, contact E1 or your local E1 distributor. So let's look at an example. The image on the right is a representation of a coastal development with connections located on various roads, and the discharge location is marked to the upper right. Each property is represented by an open circle, and the small line connecting that open circle to the road is that 1.25" or 40mm pipe. I'll mention that the hydraulic losses through that pipe are negligible in our assumptions, and generally E1 assumptions are conservative enough to absorb a lot of the minor losses that you would get through fittings and direction changes. So the first step is to ensure we have all the project information. And from this image, we have the layout. We know where all the properties are to be serviced. We have a method to measure distance. This is shown with a graphical scale, or even better if we had an AutoCAD model. We know where we're discharging. And we know what hills there might be. And I'll admit for clarity, this image does not show contour lines, but that's what we'd be looking for. The zone designations are shown here in the numbered blue circles. And again, I'm not going to review the zone designation process, and make sure you refer to other resources from E1 if you need help with that. From here, we input details from each zone into the Zone Information tab in Design Assistant. And this includes the zone number, where each zone connects, and that means like Zone 1 connects to Zone 2, and Zone 2 connects to Zone 3, and so on. The length of each zone, the number of pumps in each zone, and maximum and minimum elevations within each zone. After we input the zone information in Design Assistant, the software performs all those iterative calculations and determines an ideal pipe size for each zone, and presents that hydraulic information in table form. The left screen is an example of the outputs of flow velocity and total dynamic head, and the right is retention time. The next few slides review the E1 Design Assistant outputs in a little bit of detail. However, if you need a deep dive into how to use E1 Design Assistant, I suggest checking out the E1 webinar, Pressure Sewer Design Using E1 Design Assistant. In that webinar, we provide a very detailed review of all the inputs and outputs, including some best practices. Design Assistant calculations use commonly accepted equations to determine velocity and friction loss. Velocity calculations are a dimensional analysis. That is, we convert flow rate into velocity. And with these equations, the flow rate and the inner diameter of the pipe are known, and we're solving for velocity in meters per second or feet per second. For friction loss, the software uses the modified Hazen-Williams equation. This equation is shown, and Hazen-Williams is a simple and reliable method for determining friction loss with fluid flow in a pipe. Other methods exist, but the Hazen-Williams equation provides the quickest result with a high level of accuracy for pressure sewers. The equations shown here are well documented and available from a variety of sources, whether a Google search or your favorite dusty textbook. On the output sheets called the design pages, the software allows the user to modify pipe sizing from a drop-down menu. Upon changing those pipe sizes, the software will automatically recalculate all fields. Pipe sizing seeks to achieve a balance between three key elements: total dynamic head, flow velocity, and retention time. For the TDH, our objective is to remain below 185 feet or 56 meters, where lower is generally better. Lower the TDH reduces the load and wear on the pump and prolongs the service life. Flow velocity is what helps us ensure that any solids in the slurry remain in suspension, and buildup on the wall of the pipe is self-cleaned. This is often referred to as self-scouring, and the industry-accepted minimum velocity is 2 feet per second or 0.6 meters per second. Finally, we want to minimize retention time, and acceptable retention time does vary region to region. When modifying the pipe sizing, the software will highlight in red or conditionally format values that are below the recommended thresholds. Besides the technical objectives, pipe sizing can also be modified for regulatory or logistical reasons. For example, there might be a requirement for a minimum pipe diameter through a certain area under a roadway or railway. Also, commercially, certain pipe diameters may not be readily available, and the flexibility of the software allows the designer or engineer to modify the network to evaluate the impact of those changes. So for example, a contractor calls you up and says that the 3-inch pipe that you recommended is in short supply, and can they use 2.5 instead? We can quickly and easily find out. So, one of the most important pieces of information needed when performing a pressure sewer design is the discharge location. Remember, pressure sewer systems are collection systems moving wastewater from A to B. What we need to know is where point B is, and we need to know what point B is. And there's a ton of flexibility with discharge locations. By far the most common discharge is into an existing gravity sewer system. This is because many pressure sewer systems are utilized to service development on the outskirts of existing development. However, there are many other possibilities. In this session, I wanted to discuss two special cases. First, how pressure sewer systems can connect to an existing pressure main. Then, we will review how traditional lift stations and even E1 multiplex grinder pump stations can be integrated into pressure sewer networks. So the first advanced design concept is how we can connect a pressure sewer network into another pressure main or force main, rising main, whatever terminology you want to use. This is a common scenario when we're, say, adding a new phase, usually an unplanned phase, to an existing pressure sewer network, or when the proposed LPS network ends near an existing municipal non-LPS force main, or perhaps we're exploring different options for discharge points. In any case, the ability to successfully connect the LPS network into a pressure main is due to the high head capability of an E1 progressive cavity grinder pump. It can be very difficult to attempt to design a similar network utilizing centrifugal pumps, since there's just going to be a ton more uncertainty about the network pressure. When considering connecting an LPS network into a force main, we definitely need to know what the maximum pressure of the force main will be at the connection point, or we often refer to that as the tie-in pressure. So let's talk about the process of connecting our new LPS network into this force main. The first step is to perform the normal E1 application engineering study. From that, the maximum TDH in any zone, not just the discharge zone, should be recorded, and we'll call this point A. Next, the maximum force main pressure at the tie-in point, that tie-in pressure, should be recorded, and we'll call this point B. And as a note, if you are going to use E1's free design service, you will need to provide that tie-in pressure. A very simple feasibility can be performed. The value from point A and the value from point B must be less than 185 feet or 56 meters. This is the design limit of the E1 grinder pump, and there are always exceptions, but in nearly all cases, this is the best judge of feasibility. For those who may be using E1 Design Assistant, this can be modeled into that software package, even though Design Assistant doesn't have a specific function for it. Basically, in Design Assistant, the tie-in pressure can be represented as extra static head. So to do this in your project, enter the elevations into each zone as you normally would. Once complete, add the tie-in pressure to the main elevation at the point of discharge. This is pretty straightforward process, but being able to connect that LPS network into an existing force main will open up even more possibilities. The next advanced design topic I wanted to review is unfortunately not as straightforward. Nevertheless, integrating an intermediate or lift station is another common request. In most cases, these stations are used to help break the pressure in the pressure sewer network main. When we discharge into these stations, it's basically like discharging into atmosphere, and the flows into these stations will be pumped again. These types of stations are common whenever we start getting into higher pressures in the network. Long pumping distances create more friction, which in turn increases pressure. Large uphill elevation changes increase pressure. Even using a low C factor in the Hazen-Williams calculation can create artificial or false head in the system, which may lead to the need for an intermediate station. As we continue reviewing this topic, we will review two different but similar types of stations. We will refer to traditional lift stations to be large centrifugal type lift stations, capable of much higher flows than an E1 progressive cavity pump station. We're talking about flows in excess of, say, 40 to 50 gallons per minute. The other type of station is an E1 multiplex grinder pump station. That is, an E1 station that utilizes more than one grinder pump in a common basin. We'll discuss some similarities and differences with these approaches. So when we know that the TDH in the network is going to exceed the design limit of the pump, we need a multiplex or traditional pump station. The first thing we need to do is figure out where to put it. When using an E1 multiplex station, we typically locate this intermediate station in such a way to minimize the head on the intermediate station. When the intermediate station is receiving flows from multiple residential grinder pumps, we want the individual stations to have the higher duty if possible. That's not to say we want the individual stations to operate at the max TDH. And there's a judgment call here, and there's not a 100% correct answer, but say splitting the TDH 60-40 or 70-30 between the individual and intermediate is a good place to start. We do this because that intermediate station can be considered a critical point for the upstream system. With their traditional lift station, assuming that it's new and proposed and not existing, the location is usually dictated by other factors, including regulatory guidelines and some practical factors like available land or the capabilities of the selected equipment. Use some professional judgment to help in locating. When sizing either an E1 multiplex station or a traditional lift stations, we need to consider the number of upstream stations that will be discharging into that station. From there, we can determine the peak and the total daily flow into that station. For E1 multiplex stations, E1 provides some station sizing guidelines, and that's a good place to start. Sizing a traditional lift station is usually more a factor, again, of those external elements like regulatory guidelines or even municipal rules. There are some techniques for modeling intermediate and traditional lift stations within design assistance software. When modeling an E1 multiplex station, it's best to consider the E1 multiplex as just another grinder pump within the zone where it connects. In that zone, the number of cores in zone will increase in the station connects to by the number of active cores in the station. Additionally, the flow per day per dwelling in downstream zones is the accumulated flow into the multiplex station divided by the number of active pumps in the intermediate station. The number of active cores is shown for the most common configurations. These are the assumptions for normal operation. All pumps within these stations are capable of operating simultaneously, and E1's conservative design assumptions take that into account. But we generally design and perform pipe sizing around these typical or normal scenarios and rely on reserve hydraulic capacity of a progressive cavity pump for the atypical or emergency scenarios. When modeling a traditional lift station, E1 Design Assistant has a function for adding a lift station into the software. Under the Zone Information tab, a lift station can be added. The user can name the pump station a reference name and then tell the software which zone the station connects to. They designate the type, usually centrifugal, but again, this is just a reference field. The user can then input GPM and GPD, and the station will receive. So let's take a look at that in more detail. So here's an example of a traditional lift station that's been added to a large E1 pressure sewer system. In this case, the lift station is needed due to the high static head and long pumping distances of the project. The image on the right, this red dot denotes the lift station. And we see from the layout that this station receives flow from zone 131. And we even see that in the design where we see that zone 131 is discharging to itself, essentially discharging into atmosphere. When we add the lift station, which we call lift station 1, we know the station is receiving flows from zone 125 to 131. And we know this from reviewing the overall layout. So when adding the lift station in the zone information part of Design Assistant, we will add the max flow from this discharge zone, zone 131, into the GPM figure for the lift station. So in zone 131, we see the max flow is 88 gallons per minute. And we see in our lift station, 88 gallons per minute. We actually see our simultaneous operation in practice here, since zone 131 has 88 accumulated pumps, and 88 pumps have a maximum number of simultaneous operations of 8. And then our flow rate, 11 GPM by 8, is 88. We also see the gallons per day of the lift station is the flow per day per dwelling, which in this case is 200 gallons, times that same accumulated number of pumps, 88. 88 times 200 is 17,600. And there we go. There are the details for our lift station. From the layout, we also see that lift station 1 discharges to zone 138, denoted on the lift station details. And we can see that on the layout. It's discharging to zone 138. We can verify that lift station 1 discharges into zone 138 by reviewing the maximum flow through zone 138. So we know that the flow from lift station 1 is 88 gallons per minute. And we can also see that the flow in zone 138 is from 76 pumps. And the simultaneous operation of 76 pumps is 7. So 7 times 11 is 77 gallons per minute. That's what's flowing. That's the contribution into zone 138. And the contribution of flow from the lift station is 88 gallons per minute. And that's why we see 165 gallons per minute in zone 138. So that verifies that we've got our lift station connected correctly. And from there, the software performs the rest of the hydraulic calculations. Wrapping up our discussion on intermediate lift stations, I don't expect anyone to be an expert on how to do this just from this brief example, but I hope the key takeaways are that this is possible in some circumstances. No matter what, we need to be aware of some of the operational realities of using these stations. Those considerations may include the need for preventive maintenance, the value remote monitoring can provide, and the need to ensure we are complying as best as possible to some local regulatory needs. The second case study I wanted to review with you discusses the implementation of pressure sewers into existing residential areas where previous wastewater system is failing or inadequate. The key benefit to the municipality is the sealed resilient pipe network. An HDE pipe network is resistant to inflow and infiltration of groundwater and stormwater. That ionized strains infrastructure, increases operational costs, and increases the risks of sewer overflows. Pressure sewers can be deployed in established residential areas with minimal disruption. Installation of a pipe network with directional drilling is quick and leaves very little trace. And in the event that directional drilling can't be used, shallow depth and no grade means trenching is quick. Finally, pressure sewers allow municipalities to sewer areas that have challenging geotechnical areas. This municipal case study I'll discuss is in New Mexico in the USA. The project was an agricultural community called the town of Peralta outside of Albuquerque. Because of the agricultural heritage, water quality, and general environmental quality has been a prevailing concern. Peralta neighbors another community called Bosque Farms, and we'll explore the dynamics of these two communities next. As mentioned, Bosque Farms in the town of Peralta are outside of Albuquerque, and like many communities on the outskirts of larger cities, they were developed before municipal services like sewer and water were made available. Hence, these communities were originally serviced with on-site systems. And although it's typical to associate New Mexico as an arid desert, these areas are very fertile, with high groundwater, which was at risk of being polluted by those failing on-site systems. Now, Bosque Farms explored and implemented a septic-to-sewer project over 25 years ago. And at the time, the community explored gravity, vacuum, step, and low-pressure sewers. The life cycle cost analysis demonstrated that LPS was the ideal solution for Bosque Farms. The town of Peralta was more challenged financially, so ensuring all options were considered to find the lowest whole of lives were paramount. Engineers evaluated the same options for the town of Peralta, and their estimates are shown on the table in the slide. E1 LPS resulted in the lowest whole of life costs. Beyond whole of life costs, the success of LPS at Bosque Farms certainly helped the justification at the town of Peralta. The town of Peralta was able to connect the first 300 customers within the first 12 months of the project, and connections are ongoing. Another noteworthy dynamic of this project is that the wastewater treatment plant in Bosque Farms accepts the flows from the Peralta LPS system. And this intermunicipal arrangement was made possible in part due to pressure sewers' inherent resistance against inflow and infiltration. Had Peralta used a gravity sewer, the amount of inflow and infiltration into the gravity system may have exceeded the available capacity at that treatment plant. At the end of the day, the town of Peralta have embraced the project. The system protects the environmental quality of life for the entire region and agricultural industry. Hey, and if you appreciated these case studies, I want to make a special plug for the E1 catalog of video case studies. Check out the E1 website or visit the E1 Sewer Systems YouTube page for a collection of beautiful and compelling case studies. Let's talk about the construction of pressure sewer systems. Typically, I like to look at the construction of a pressure sewer system in two phases, the off-property construction and the on-property construction. Off-property primarily deals with the construction and installation of the pipe network, valves, fittings, etc. And it's nearly always in public property, in a utility corridor, the street, the right-of-way. The on-property portion deals with the installation of the grinder pump station and alarm panel. The off-property construction begins with the system piping. And HDPE is the most common and best performing, but PVC is still used commonly. There are a variety of pipe diameters commonly produced, and installation of the pipe network can be completed using open trench methods, which are more common with new construction since there's other services being installed, or those trenchless methods like horizontal directional drilling, which is more common when we're installing systems into established areas. There are a variety of other valves and devices which can be found in the pressure sewer system. Flushing connections are recommended at points where the main can be cleared with jets of high velocity and high volumes of water. The diagram here is a general layout from E1, and these are typically assembled by the installing contractor using approved local components. And E1 generally recommends flushing connections are at branch ends. Branch connections in every 1,000 feet or about every 300 meters. Division or isolation valves are also commonly found in pressure sewer networks. The type of valve and placement follows local requirements. Division valves are incorporated in flushing connections, so commonly you find them together. And division valves provide a means for system isolation to facilitate maintenance activities. And division valves are also commonly used during construction to allow phasing of a system. Air is going to be introduced to the system every time the pump cycles. And as air accumulates, it can add resistance to flow, which is going to increase the load on the pump. And to help relieve the extra load, air release valves are recommended at high points and where there's an elevation change. And these devices allow that air to escape. Vacuum release valves are used before downhill runs, also to prevent damage to the system due to negative pressures. The on-property installation is pretty straightforward. Locate, excavate, install, connect, bury. Grinder pump station should be located in a position where the aesthetics of the cover can be integrated into the existing or new surroundings. And the cover of the station must be accessible, but they're often located in landscaped areas. And then the alarm panel is typically located within line of sight of the grinder pump station. Installing an E1 station is not difficult. In fact, we purposely designed it to be easy, but E1's learned that the system reliability is a function of the quality of the installation. E1 has installation instructions, installation videos, and even a certified installation program for contractors. System operation and maintenance is often a source of uncertainty and doubt to those new to pressure sewer systems. Faced with the potential of many pumps, many initially believe that the cost and manpower needed to maintain the network is immense. However, that's a myth that E1 strives to dispel. In this section, we'll review some of the basics and expectations. The E1 equipment is purpose-built to be as serviceable as possible. The core concept integrates everything to a single unit that's easy to install and replace. The electrical connection between the grinder pump has a large purpose-built quick disconnect plug, and this creates a simple and reliable means to disconnect power to the pump without tools or an electrician. The stainless steel components are more robust than many of their PVC equivalents. And finally, the design of the alarm panel versus a control panel means that those critical starting components for the pump are protected. Also, a fault in the panel does not mean that the pump will not operate. That reduces risk. When we examine operation and maintenance, the two key metrics are mean time between service calls and cost per pump per year. Cost per pump per year is a pretty straightforward calculation. Total expenditure divided by number of pumps operating. The mean time between service call can be applied over a long period of time to see, on average, how frequently each pump needs to be serviced. This slide shows some examples of data collected from systems around the world. E1 expects the cost per pump to be less than, say, $50, $75, and the MTBSC to be 8 to 10 years. These numbers are for properly installed and operated systems. Systems which are subjected to a lot of user abuse will have higher costs. E1 and our distributors can provide support to projects struggling with their operation and maintenance, and we've had a lot of success working with users to improve performance. Our operational data, though, comes from sources all over the world. Really, data drive our performance and reliability claims. The final section to review is how we assign a life cycle cost to pressure sewers and other options with the goal of determining what is the best solution for a particular project. One of E1's key objectives of the life cycle cost exercise is to challenge assumptions and dispel myths and misconceptions about pressure sewers and other collection systems. For gravity systems, it is so common to hear that once they're installed, they're free to operate. And this is simply not the case. Gravity sewers require constant maintenance on the pipe network due to cracks, separation, deterioration, root infiltration. Also, most gravity systems have large major pump stations, which require routine maintenance. Gravity systems invariably begin to leak and allow groundwater and stormwater into the system. And the cost to transport and treat those extra flows increase the operational costs. Simply put, gravity sewers are not free. Vacuum systems, they commonly make a lot of the same claims of pressure sewers that they're sealed. And while this might be the case on some systems, on others it's not. Just the sheer number of pipe fittings in a vacuum system is about 10 times the number of a pressure sewer, and each one of those fittings is a potential for leak. Another misconception about vacuum systems is that many homes can share a common valve chamber. This often results in long, deep private drainage just to reach that valve chamber. And this creates a lot of vulnerabilities in the network. For pressure sewer systems, the common misconception we receive is that they're maintenance intensive. And as we've already reviewed, this just isn't the case for E1. E1 has created a lifecycle cost calculator tool to assist you in making comparisons. And our objective is to ensure that pressure sewers are considered and evaluated based on actual merits instead of being disqualified because of the myths and misconceptions. The tool outputs a present worth value for the options under comparison. Simply put, the lower the number, the lower the lifecycle cost. As stated, the outputs of the lifecycle cost calculator tool provide this high-level comparison of the options. And in this example on the slide, pressure sewer's present worth is about 3.3 million compared to the gravity sewer of about 4.4. Again, the purpose of this tool is to aid the user in the evaluation of the different options and ensure that proper consideration is given to the real operational costs, not just assumptions. Pressure sewer is not always the best option, and every project's going to be different. Look, the best part of this tool is there's no risk in using it, or Design Assistant. Both are free and available at e1.com. Whew, we have reached the end. Congratulations. Look, again, I'm really pleased that you took the time to be with us today. I hope this webinar has demonstrated E1's passion for pressure sewers. We are the originators, the innovators, and the leaders of this market. And hopefully during our time, you've learned more about pressure sewers and understand that they are a widely used technology that can help stakeholders solve a variety of problems. And the systems are commonly used in new land development, septic tank replacement, and to fix failing other systems. Also, life cycle cost analysis should be conducted when we evaluate what option is best. And finally, that the operation and maintenance of a pressure sewer system can be cost effective and efficient. You know, with that, I am joined by two of my colleagues, Mike Crowley and Nick Shafarzik from our application engineering team. And Rach, I'm going to hand back over to you to see if you have any questions from the audience for us.
Okay, and Derek, thanks for that excellent and enthusiastic presentation. Maybe take a few sips of water, deep breath. That was great. Thank you so much. As promised, we'll start right in our Q&A session. And as a reminder, if we don't get to all of your questions, we'll answer them in a follow-up email. So here we go. How many households do you recommend be limited to a single grinder?
So in general, we believe that the best method is that a single house connects to a single grinder pump station. You know, there have been projects around where people have connected multiple pumps to it, and it's logistically, or excuse me, technically it's possible from a flow standpoint. I would just put out there that there's maybe some logistical things to consider, such as where the electricity is going to come from, and in the event of an alarm, you know, where does something like the alarm panel get mounted? So there are some externalities, if you will, that need to be considered when you're figuring out. So because of that, just the simplest thing, the most straightforward solution is just a one-to-one.
Okay, thank you. Can any contractor install these E1 pumps?
Look, I think any contractor has the capabilities to install the systems. And as I reviewed, they're not exactly difficult. There's definitely some do's and do not do's. And so what I would encourage is that any contractor receive some amount of training from E1 or our distributors about the proper process about installing these systems.
And what happens during a power failure in the subdivision? We received this question a bunch of times.
Well, I live in Texas, and so we had a bit of a power outage recently. So look, very simply, the pump doesn't work when there's a power outage. And this is where we have to start thinking about what contingencies are in place, the likelihood of a power outage, and the likely duration of a power outage. You know, in general, a grinder pump station has some inherent storage capacity within a tank, within the basin itself, and that's generally able to deal with your, call it the 90 or 99% of most power outages. When you have extenuating circumstances, multi-day, seriously long power outages, you know, then you have to start looking at some other means. E1 has alarm panel options that have emergency generator receptacles on them. I'd say in areas that are prone to routine power outages, certainly not where I am, that was a bit unusual, but say in the southeast of the US, when you got hurricanes that come through periodically, having provisions for emergency power, or if a property already has a generator, they're taken care of. And in the most extreme situations, when you do have long durations, we've seen projects where grinder pump stations can be powered with a generator that's on the back of a truck, or the stations can even be, the lid of the station can be taken off, and a vac truck can be used to suck out the contents of the station.
Okay, thank you. Are the check valves, integrated valve in grinder pump, as well as the one in the discharge pipe, susceptible to jamming from the ground waste?
Not usually. One of the reasons why we use flapper non-return valves or check valves versus other valves, specifically ball check valves, is because of our experience in how resilient a flapper non-return valve is. Maybe the question was about ground debris or ground waste. Again, I'm not 100% sure if that's about the susceptibility of the materials of it, or just ragging and things like that. But it's been E1's experience, the design and the materials that we use in our check valves are suitable in most every application.
Okay, and Derek, as you know, E1 manufactures both an interior unit and an exterior unit. This particular question is in reference to our indoor unit. Pros and cons of it, please.
So we have units called the indoor unit, which actually come in a variety of configurations themselves. Typically we see these indoor units in the northern areas of the continental US, where you might have might be easy to retrofit an indoor unit into a septic-to-sewer project. Indoor units don't require excavation out in the yard or a piece of property. So there's a variety of pros and cons specifically. Functionally, technically, they're practically identical. They have the same pump, the same hydraulic, the same grinder. So it's really just, the feasibility and logistics of where the drainage in the house is and where the discharge for the pressure sewer network are.
What is the size of a grinder pump, and will this pump generate any dynamic load on the ground, like ground shaking?
So the physical dimensions of a grinder pump, great question. I'm trying to think off the top of my head. Square, they're probably 18 inches if you take like an 18-inch in diameter cylinder, and it's depending on if we're talking about the grinder pump or the entire station. Sorry, the entire station is normally between 24 and 36 inches in diameter. We'll call it 700 to 800 millimeters in diameter, depending where the question's coming from. And then they can be a variety of heights. I'm not aware of any ground shaking that E1 stations create. I will note, because we have a progressive cavity pump versus things like a centrifugal pump, we don't have a big impulse during startup. That helps by to not only reduce the mechanical load and abuse on the pump, but it also really helps with the noise as well. An E1 grinder pump is practically silent compared to, certainly a centrifugal pump. But yeah, so again, I'm not really familiar, or haven't heard any complaints about any ground shifting or seismic activity from a grinder pump station.
So how about addressing odor control in these systems, especially in vacation homes?
Yeah, so under normal circumstances, the E1 stations are designed to cycle frequently. The levels inside of the station are predetermined to have the pump cycle regularly, and that aerates, stirs the sewage to prevent that septicity from occurring. Now, in these seasonally occupied areas, you get large periods of inactivity, and there's a couple of first up, there's the best mitigation for that is some behaviors. So, some general recommendations for people is before they say leave for the season. So say this is a house in Florida that is occupied during the winter, and then come, April, May, June, the residents leave and move up north where it's not as hot. Our recommendations are generally to run water, and that helps flush out any of the kind of the organics in the station that could create an odor. That could be running a tap for a little bit, or filling a bathtub and dumping the bathtub. You're almost now the inverse of winterizing it. You're summerizing your grinder pump station. You can do the same thing regardless if it's a winter or summer property. In general, I will say that if odors are created, or if you don't do that, our general experience has been that the odors are noticed when someone returns to that property and then starts using water, and it starts displacing the, potentially the hydrogen sulfide gas that's in that station. And so generally it leaves pretty quickly once things have had a chance to go back to normal. But again, kind of that mitigation, the easiest, lowest hanging fruit is just to flush the system before you leave for the season.
Okay, what needs to be factored in when the LPS system runs uphill, crests, runs downhill, and then continues uphill to its discharge point to the municipal gravity system? That's a heavy question.
Yeah, it is, and that's why I'm going to hand it off to hey, Mike Crowley. Do you want to pick up that question? If he's still on.
Yeah, he just unmuted.
Sorry, Derek, what was the question again?
Okay, what needs to be factored in when the LPS system runs uphill, crests, runs downhill, and then continues uphill to its discharge point to the municipal gravity system?
You basically just need to figure in what's the change in grade from your grinder pump station to your highest point, and that's how you would calculate your static head. Any intermediate change in grade in between does not really matter, as the pump has to pump over the highest point.
Any air management in that situation, Mike?
If there is a change in grade of 20 to 25 feet or greater, an intermediate high point somewhere along that run, then we would typically recommend a combination air vacuum release valve at that location.
Okay, thank you. And thank you all so much for attending our presentation. It looks like actually we've just run over on time here. So on behalf of all of us at E1, we thank you for joining today's session, and we look forward to seeing you soon. Please check out our follow-up email, which will contain answers to the questions, a PDF of the presentation, lots of cool stuff to look at, like our design assistant and life cycle cost calculator. And most of all, be well. Thanks.